In a previous lecture, we discussed the self-assembly of amphiphilic phospholipids into bilayer structures. Phospholipids can exist in different phases, ranging from micelles to bilayers to hexagonal cylindrical phases. Lipid bilayers are of great importance since they provide the fluid structure that is so important for the proper functioning of cell walls. Lipid bilayers can themselves exhibit different phases depending on the temperature and the characteristics of the amphiphil. At low temperatures, hydrophobic tails develop an all-trans structure that allows their efficient packing with crystalline order, thus forming a structure we call the gel phase. The van der Waals attraction between neighboring lipid molecules is stronger when the lipid tails are longer, in analogy with the observation that both the melting and boiling temperatures of alkanes are higher for longer chain alkanes than for shorter chain ones. At higher temperatures, where the thermal energy is large enough to disrupt these van der Waals interactions, the hydrophobic tails of these lipid molecules develop disordered conformations that prevent their packing. Under these conditions, the bilayer structure exists in a more fluid, liquid crystalline phase. As discussed above, the stability of the crystalline gel phase increases with the length, that is, with the number of carbon atoms in the tail. For instance, while the gel to liquid crystal transition is observed around room temperature for a 14 carbon atom tail and around 65 degrees Celsius for a 20 carbon atom tail. Obviously, the proper functioning of cell walls requires a sufficient amount of mobility in the lipid bilayer structure. Molecular mobility in the bilayer structure is necessary for both the ability of cells to deform mechanically and for the facilitation of molecular transport through the membrane. The phenomenon of endocytosis, for instance, could not take place with a rigid crystalline membrane. When we talk about saturated membranes, we are referring to the fact that membranes are made up of fully saturated lipid molecules. A careful examination of naturally occurring membranes indicates that they are not made of pure phosphatidylcholine lipid molecules. Membranes are often asymmetric, with different molecules on the inner and outer part of the membrane. Membranes often contain cholesterol molecules and unsaturated lipids. These molecules disrupt the packing of saturated phospholipids, provide an increase in free space and mobility in the membrane, and allow precise control of the membrane gel to liquid crystal transition temperature. For example, as shown on the graph on the right-hand side, adding one unsaturation or double bond in a phospholipid with 19 carbon atoms leads to a decrease in the melting temperature of the phospholipid bilayer by over 50 degrees Celsius. A good example of this effect is the difference between butter, which consists of mostly saturated fats, and vegetable oil, which has a large concentration of unsaturated lipid molecules. The larger the number of unsaturations in the lipid molecules, the larger the number of kinks in the structure, the less efficient the packing between these molecules, and the lower the melting temperature.